This is the Tesla switch, which isn't really a switch, and it's not really, I don't know if it's really Tesla, so I can't say that way one way or the other, but it's frequently referred to as the Tesla switch. The whole function of this thing is to show you that potential is arbitrary. You can draw a charge between two positive poles, or you can draw a charge between two negative poles, so long as you frame the context correctly. Meaning that if you want to draw a charge between two positive poles or between two negative poles, you have to set up the two poles so that they are offset in their potential relation to each other. And to that end, that's why we end up with the series bank and a parallel bank. I tend to call them series stack and a parallel stack. And the switch isn't the fact that there's a switch on it. The switch is the fact that you run it this way to discharge this load, which is a light bulb, to illuminate the light bulb for so long, some period of time. While it is running the light bulb, this stack discharges, this stack charges. After some arbitrary time, based on probably current consumption and volt drop off of the series stack, you then shut it down. These get wired in series, these three get put in parallel, and they trade places. That's the switch. And then you power it again for some period of time. And in theory, this is kind of like Tesla's shuttle circuitry, which is where it just oscillates the charge back and forth between two storage containers or capacities. And this is sort of that ideal. So that's maybe where that reference comes from. Anyway, we'll turn it on so you can at least see it run. This is just static, so it's a DC discharge, single switch. There's no oscillator, nothing else going on here. It draws about 500 milliamps. This is a 0 to 1 amp ammeter. This is a 3 volt flashlight bulb. Which explains why I used 6 batteries in total instead of just 4 batteries in total. I needed a 3 volt relative potential. To achieve a 3 volt relative potential, I have to build on top of the parallel stack, which actually includes that bottom series stack battery, the 3 volts, which is up here. If I only needed 1.5 volts to light the bulb, I only would have needed that battery, and I would only need 4 batteries in total for 1.5 volt difference. As the relative potential. However, silicon electronics tends to need at least 0.7 volts to 1.2 volts to be able to switch itself. And, as a matter of fact, you can run transistors with this type of a configuration, with both charges being between positive and negative, or sorry, positive and positive, or negative and negative. In this case, the ammeter is between the two positive poles, and the load is between the two negative poles. So there you have it. That's the Tesla switch, or the relative potential configuration. How to generate a relative potential.